Welcome back to another machining video. In an earlier video on this Proxxon FF230 teeny tiny mill, I made some vise hold downs for this QGG vise. You can check that video out. In this project, what I would like to do is extend the functionality of this vise by adding a vise stop to this M5 threaded hole right here. What a vise stop will do is allow me to position a part repeatedly on the x-axis in this vise. Now, presumably, you've already seen the thumbnail for this video, and you know what the end result is going to look like. I don't know yet, but I have some idea. I made a blueprint of it right here. I really want to do this in Fusion 360, but my computer just wouldn't handle that software. So I'm using something a lot more deprecated and old and crusty, and that's what I got. Anyways, here is the jaw of the vise, and that is the design I'm looking for. I had to render it for a little while, and well, there it is now. Maybe I'll come back to this diagram a little bit later on, but for the moment, what I need is almost a square, a rectangle of metal, 21 millimeters by 23 millimeters in size. Now, where am I going to get that? In the previous video, I used square stock 416 stainless steel, rather expensive stuff. Here, I'm going to use some bar stock. This here's 3/8 by 1.5 inches, and this is available a fair bit more cheaply from knife suppliers, knife-making suppliers. Knife makers, they like this stuff because it polishes up at machines easily. It has some corrosion resistance, moderate for stainless steel, and yeah, they sell bar stock not too bad of a price. There's quite a few different suppliers out there that are able to supply this to you. Anyways, let us cut out a 23 by 21 square of material. Let's put that down like so. Now I got here a scriber gauge set up to 21 millimeters, and I'll just mark that with a Sharpie. Like so. It's a thick Sharpie. It's going to be about a millimeter and a half thicker than 21. Now let's set it up to 23 millimeters. That looks not too bad right there. And there we go. Now off to the bandsaw. So here's the stock. I now marked it with a Sharpie on 3 sides. And it's mounted in a vise. Let's make sure it's good and properly tight. I'm just going to be cutting it here with a battery-operated bandsaw. It's not super accurate, but I find that freehand I can usually keep it within that Sharpie mark, and then that can be just cleaned up on the mill without too much issue whatsoever. And the next side. So here's our part, rough cut. We got to clean these cuts up with the mill. I'm going to do each one of these 4 sides first, get it squared off, and then just take a whiff of material off the top and the bottom of these 2 flats, and then I'll have a part that is roughly 23 by 21 millimeters by about 3/8 of an inch. Now, I do notice a minor problem with this little bit of bar stock that I'm going to have to keep aware of. Yeah, at some point it must have been dropped and this corner here is mushroomed. So I'm going to mark that just so I know to be careful with it in my clamping setups, because otherwise it's not going to clamp nice and flat. Oh, let's get it set up. Well, that mushroom corner might not be too much of a problem because it fits nicely here into this V groove on my vise. Just got to remember to position it in there well. Let's tighten it up and see if those parallels are nice and snug. Good to go. Now, like last time, I got my swarf corral installed, and they magnetically clip onto the table and helps keep the chips in a little bit more neat of a fashion. Now, the last time I had a swarf corral piece on a vise, protecting the lead screw from chips. However, I found a little bit of a annoyance with that, and the annoyance was that the chips that were coming off of this 416 steel, this is a magnetic stainless steel, the chips were magnetized and they stuck to everything. It was really, really annoying. I did a little bit of research, and it seems that when steel is struck, it's shocked in the presence of a magnetic field, and you can see it here on this field viewer, that the chips become magnetized. So I'm going to not use this Swerve Corral piece over the lead screw this time, and instead I'm just going to have to clean up the lead screw regularly. Do proper hygiene, I suppose. Anyways, I got the ESC bit installed like the last time, 3-fruited variety with 0.2 millimeter radius. But unlike last time, I'm going to use a bit of a different speed. The last time I was going at maximum speed, around 2200 RPM nominal, and this time I'm going to try it at 1500 RPM and see if that helps out a little bit with the chatter and gets a bit of a nicer finish. Evacuate the focusing form to a safe location. Make sure this is at 0, and find the surface. Pretty good. Advance 1/10 of a millimeter. Lock down this axis. And okay, that's a start. That was a millimeter in and should be the last pass. And that finishes up the obverse. Third side, my wavy bandsaw cut. This is going to take a couple more passes. And that should be the last pass of the fourth side. 4 sides done. Now let's get the 5th and the 6th just to clean up that mill finish, just to take off a whiff of material, maybe 1/10 of a millimeter, maybe 1/20 of a millimeter, not sure. Anyways, I had to move this vise inwards a little bit, and I used these clamps. Check out that video I made of these, the last machining video I made a month or so ago. These are really awesome. On my first try, I got the vise trammed within 1/1000th of an inch from end to end, and on the second try, it took very little time at all. I got it trammed to, well, it's sub-100th of a millimeter precision. Now, for this project, I don't need that, but it's fucking cool nonetheless. And here's our finished part. Let's check out the dimensions. On that axis, we got 23 millimeters on the dot. Here we got 21 millimeters on the dot. The thickness is not that important, but for posterity, we got here 9.4 millimeters in thickness. Now, insofar as fit and finish, Lady Chatterley betrayed us again, and there's a little bit of chatter here. It's not the nicest finish, but you know, it's, insofar as I'm concerned, it is completely acceptable. This was milled with an ESE end mill that uses carbide inserts with a little bit of a radius on them. It makes these ESE bits just last forever and ever, and you can really abuse the hell out of them, like using them on a tiny mill, which is very, very shaky. It's not really rigid. It's not really rigid enough to use it with a proper carbide bit With proper carbide bits, you do get a much nicer surface finish. However, the corners tend to chip, and these cost money. Anyways, I still like these ESC bits because they're durable. Next up is to put some precisely placed 5mm holes here in this workpiece. Now, putting a hole in an exact location, it's not straightforward because twist bits, they're notorious for not going where you want them to go. They veer off a track, and they can go at an angle, and yeah, it's not good. You need to actually build the hole up in size. You got to start with the pilot hole and get a bigger hole and a bigger hole, and so on and so forth. Now, on top of that, this mill throws in an extra curveball. An extra curveball is, well, you got this travel here, which is reasonable. However, if you need to readjust the height of the power head to accommodate a different size drill bit, well, then you got to loosen up this column block. And there's a lot of play in that column block, and when you lock it back down, it might be off by 0.5 millimeter or even more than that. So we need to get this set up in a way to use all the tools that we need just with the quill feed. I have a set of tools here that we'll be using, as well as the collets, get them all nice and prepared and ready to go. We got a 3mm end mill, and the end mill is going to not veer off a track. It's going to go nice and straight. And then I got a 4mm bit, and that's going to continue the hole through the pilot hole the end mill drilled, and that'll just expand the hole out a little bit. Then a 4.9mm drill, and then lastly a 5mm tap. And then on top of that, I almost forgot to mention, we need an edge finder to actually know where we are. And to give us a fighting chance of getting these holes exactly on location, I blued one side of this workpiece with a blue Sharpie, and I scribed it using this handy-dandy scribing gauge and a very fine-pointed scribe in order to locate where the holes should be. Here should be one right there at that crosshair. And there's a 5mm bounding box there that will allow us to, well, verify the accuracy of the hole placement. We need a hole right there, a hole right there, right there, and right there. Now, I did change my design just a tiny bit. Let's go back to the blueprint. In an earlier blueprint, rather than 2mm, that was a 1.5mm wall thickness. Well, I'm going to go with 2mm. The main reason why is, well, these little parallels that I have, they're about 1.5 millimeters, just a little bit more than that in thickness. And, well, I need a little bit of clearance to make sure I'm not crashing a drill bit or the reamer into my parallels. Let us locate our first hole with the help of an edge finder. An edge finder is this tool that has this eccentric, spring-loaded eccentric at the working tip. And let's see how this works. You turn the mill on at the lowest speed, and you can see that eccentric tip is wobbling around like that. Now, on the y-axis that we're going to zero the y-axis with the fixed jaw of the vise, which is effectively that side of the workpiece. And we're going to get this zero properly right there. That's good. And I'm going to pull the y-axis outwards until that eccentric starts, the center finder starts touching the fixed jaw. And you can see that the eccentricity is decreased, and it looks like it's almost perfectly now running true. However, where you find the edges, you keep pulling it out until right there it kicks out. Now we can turn that off, and what that means is that we found the edge of this, well, not really the edge of it, the spindle is 3 millimeters away from this edge because the thickness of this tip is the diameter 6 millimeters, 3 millimeter radius. Okay, so now let's go back to our blueprint. We want to find the center of that hole right there. We're currently 3 millimeters in from that edge. We need to go another 1.5 millimeters. So let's do that. To do so, we need to push the y-axis in. There is a little bit of backlash there, so I got to compensate for that. And now we can move this in one hand wheel revolution. That's 1.5 millimeters. And that's pretty good right there. Now we can lock the y-axis down, And let us find the this edge of the workpiece. Kick that out again. Kick the center finder out. Turn it on. Let us get this zeroed on the X. That looks pretty good. And now touching the workpiece. Eccentricity is decreasing. And kicks out. Okay, now that is 0. We now need to remove the edge finder and spin it out like so. Okay, edge finder is out of there. We are currently 3 millimeters away from there. We need to go in 3 millimeters plus 2 millimeters plus 2.5. That would be 7.5 millimeters, which would be 5 revolutions of this hand wheel. Each revolution's 1.5 millimeters. So let us pull the x-axis that way. That would be 1.5. That would be 3. That would be 4.5. That'd be 6. And now I'll do a little bit more slowly until we get that 0. Now we should be 7.5 millimeters, and that's going to put us exactly where we need to be right there. I installed the 3 millimeter end mill. I don't have the fine feed engaged anymore, just using the quill lever. Got the mill set to the highest speed, 2200 RPM. And let's just check here. It seems like it's on the money. It should be. The hand wheels are really quite accurate. The main issue with using hand wheels is just simply not doing your arithmetic right and miscounting revolutions. Really easy to do. But in this case, we seem to be on the money. So let us turn it on. And let's just mark that hole. And just double check. Does it look like it's in the right place or not? That seems not too bad whatsoever. So let's do a pilot hole. 3 millimeters. This is a really sharp carbide bit, and it cuts through this easy to machine stainless steel really quite nicely. Bit is not installed in the collet very deeply, however. I'd prefer it to be a little bit deeper, but it needs to be there. Otherwise, I would need to be moving the power head up and down, and, well, as was discussed a little bit earlier, that's problematic. Okay, there is our pilot hole, and it really does seem to be right on the money. Awesome. Next is a 4 millimeter drill bit, and I'm going to use a dribble of cutting fluid. Speed is slowed down. And this is going straight through. Make sure that I'm going to... Still slipping. I'm going to try speeding it up a little bit. Okay, sped it up now to about 500 and some odd RPM, so maybe that'll be a little bit better. Yeah, that's working better now. Small bits, they need higher RPM. Okay, that's 4 millimeters through. And the hole is still nicely centered in the bounding box. Let's move up to a 4.9 millimeter bit. That is through. And lastly, a 5 millimeter ream. Next hole, 3 millimeter end mill. Third hole, 4 millimeter bit. Fourth hole, 4.9 millimeter bit. And a 5 millimeter ream. Now that these 4 holes are drilled, I need to convert these 2 holes into a slot. Now to that end, I've installed a 4 millimeter high-speed steel end mill. However, the quilt doesn't have enough travel to get it all the way to where I need it to be. So unfortunately, I'm going to have to loosen up the column block and lower the power head to a bit more of a useful location. Seems about right there is good. Let's tighten the column block back down, and can't really tell, but it still seems to be more or less centered. Now let me off camera do a little bit of arithmetic and see how many hand wheel jogs I need to do to put that bit smack dab between these 2 holes. And now we're centered between these 2 holes and ready to plunge. Now that completely borked this end mill. You can see that this tooth here and that tooth have been sheared off. At least the side's still in good condition, and this hole is started, so maybe I can finish it off with a 4 millimeter drill bit. Seems to be guiding true. All the chips are falling through those 2 side holes underneath, and we're through. I got that 4 millimeter end mill reinstalled, the quilt is locked, and hopefully we are ready for some side milling. A bit squealy, but it worked. Now it's going to move the x-axis just a little bit, a fraction at a time, and I'll just got to smooth out the side, and well, I got a slot. Let's do that. Let's unlock the x-axis and turn the mill on. I'll advance it like, very, very little. It's like 0.05 of a millimeter. Again, 0.05 of a millimeter. Here's this part now drilled and slotted. I'm really quite happy with this job. I had to finish the slot off a camera because it required a lot of care and attention. I need to listen to the mill, hear what it was doing, get my eye up good and close. I had to get the camera out of the way. Anyways, that's one deep slot for such a tiny mill in steel. All of these holes and that slot are dead on accurate, at least within the precision of these scribing lines I'm showing here. So here's one scribing line making a bounding box for this hole. Here's the scribing line for the slot. You can see it maybe a bit better down here, and then across like so. And over here, this one is a little bit more difficult to see, but there it is for right there and across. That is really cool. Anyways, awesome. Now off camera, not too interesting, I did a pass with the ESE end mill just to prepare a new surface and obliterate all the scribing lines. Yeah, I couldn't help but notice in some of these video sequences that it looks like this finish is really quite rough, but it's actually not. It's really smooth to the touch. Now, right out of the mill, the holes were definitely not smooth to the touch. They did have a little bit of a burr. Now, that burr could be removed quite easily with a deburring tool like this Noga variety here, and the way you do it is you just rotate it around like so, and I already did it, and let me just twist the you can see it right there, twist the part in light, and you can see how the edges are relieved. Anyways, what we need to do now is make some holes right here. We need an M4 hole, well, a hole that would be tapped for an M4 screw, 4 millimeter clearance hole, and a 7 millimeter counter burr. And here's the dimensions of the top of the part. And just like before, I use the scribing tool and the scribing gauge just to make a bounding box and some crosshairs just to verify. I'll still, again, I'm going to use the hand wheels to get it nice and precise, but it's nice to have that little bit of insurance, make sure I didn't screw it up. Anyways, as before, I got my ducks in a row here, and I got a 3mm end mill there, 3.2mm bit for an M4 tapped screw hole, a 4mm bit, a 7mm end mill, and a counter stink bit for making a light chamfer at the end. Of course, we also need the edge finder and our assortment of collets. Okay, we're in location, we're verified, and I got the 3mm end mill in. The end mill is a lot more properly located in the collet, so you can see the runout is no longer as much of an issue as it was before. Let's plunge this 4.5mm until we make contact. And contact 4.5mm, that would be 3 cranks of the fine feed. Now a 3.2mm bit, I gotta sink this in at least 9.5mm. 4mm bit, gotta sink this one 4.5mm. And now a 7mm counter bore, sunk 3mm. And that's 3. And now just a very light chamfer. I do it. Stressful. And here's our part, and I do think that this hole turned out quite nice for the M4 screw. The next thing that we need to do is we need to cut out a square material here. So I scribed some lines to help us set it up with a slitting saw. I got a 1mm slitting saw installed, and I have it set up so that it will be cutting just above my scribed line. Here's a scratch mark I made with it. I added another scribed line along here so that I know how far to take the cut inwards. I'm doing this a little bit shy of the scribed line because I don't know how straight the saw is, and I'd clean it up on the mill anyways, even if it was a pretty good cut. Well, let's get going. Almost finished this cut. I'm feeding it about 1/4 millimeter at a time. Second cut, just like the first. So the slitting saw ran true. I only need to remove about 1/3 millimeter of material. And here's our part finally dimensioned. I cleaned up these 2 slitting saw cuts. It took about 3 passes with this mill. And now we are ready to tap this hole. There's a bit of a short-sightedness in my plan, however, and I did not count on this hole being so close to that surface. Now, to properly tap this hole, a tap is going to need to stick through there, and the tap might be marking that surface up. I'm not certain whether we'll be able to do this without that problem. So let's lock it here in the vise. I got a first tap here, and then here is a second and a third tap. You can see the difference between these is this one is for guiding and starting the tap, and the next one is for continuing and cutting the threads further. And the third tap can get the threads nearly to the bottom of the hole, not quite all the way to the bottom, however. Anyways, let's get some cutting fluid here on the tap. And I'm going to cut this sideways. I rarely do that. It's kind of hard to make certain that I'm perpendicular to the hole. But I'm going to do it this way because in the video camera I can actually see, well, the tip of the tap coming out of that hole. So let's get started here. The first tap is supposed to be self-guiding, so hopefully that is the case. Seems to be going in straight. Getting a little bit of resistance now. Oh, some chips are coming out the rear end of that hole. Get a brush and just keep those chips at bay. Okay, I can't make that tap come out much further, or else it's going to start marking that surface. I guess it's only cosmetic. If I really needed to, I could just mark the surface up and call it a day. Let's see if I tap it that deep for the second and the third tap, maybe that'll work. Okay, let's now take the first tap out and load it up with a second tap. A little bit of resistance. It's cutting threads now. And again, I'll make the tap come out maybe about that much for now. And now a third tap, also known as a bottoming tap. Supposed to be able to get to the bottom of a hole. I'll go about that far, maybe just a little bit further. Okay. And now let's check it with the screw and see how much the screw was able to thread in. That might actually work. It threads almost all the way to the bottom of that hole. Awesome! Let's bevel some of these edges. I have a chamfering jig installed on my belt sander. I made this some time ago. I have a video. You can check that out there. This chamfering jig makes it really easy peasy to put a bevel on small parts such as this. However, unfortunately, it would be rather difficult to use this jig to put a chamfer on an inside angle like that. It just wouldn't work. However, I can do some of these edges, and I figure I want to do that edge, that edge, that edge, and that edge. With the jig, I can do 3 of those, and with the other 2, I will have to figure something else out. Anyways, let's just see how easy this is to use. And there we go. Now to do this edge and that edge, I'm going to have to do it without my jig and instead just use the table. I made sure the table is nice and square with the platen, and I have an angle guide here, and that will allow me to slide the workpiece into the belts, into the sanding belt. Okay. Not bad. The final machining act is to saw a slit across the midline between these two holes and through the surface here. I got a 1/2 millimeter slitting saw set up, and I got an edge finder for X and Y, but I don't have a good height finder. I did my best to rest the saw up on top of the part, then I moved it off. I used the fine feed mechanism to get it about where I wanted. However, I wasn't entirely sure that was accurate or not, so we can double check it with some gauge blocks. I have here 4.25 millimeters of gauge blocks. You can just rest that there on the saw like so. And if it's in the right position, it should be even with the top of the workpiece. And, well, we can tell that just by tapping this other gauge block on top. And after I did the hand wheels, it wasn't. I fiddled around with it a little bit, and it was off by maybe a 0.1, 0.2 of a millimeter, something like that. And then, of course, I scribed some lines here just to be extra certain that there shows a 1/2 millimeter of curve right in the middle. Well, let's just test it out and touch the saw onto the piece, and well, if it's not in the correct location, there might be a little bit of a wound. Well, apprentice mark, I suppose. Let's see. Let's see, is that mark? Oh, perfect. Awesome. Let's do the job. Now the machining is done. All that I needed to do was clean up the burr left behind by the slitting saw on the inside of these holes. Could be done easily with a very small needle file such as this. I already did that, and now solely for cosmetic purposes I'm going to throw it in the tumble vibe for a little while, and that'll make it nice and, well, get rid of all the mill chatter. Alright, put the lid on. This thing is really quite the racket maker. So I'm going to run it for maybe, I don't know, 12 hours or so and vacate the room until it's done. Here's a 5mm ground rod. This is in 303 stainless steel, another free machining variety. Now I cut this to length with my hand bandsaw, and yeah, it's not the best cut, so I'm going to clean it up on the mill. I have here a carbide 10mm bit installed. I showed it earlier in the video with some chipped teeth on the bottom end. However, from experience, I know that the side flute side milling for this mill works quite acceptably. Here's the rod correctly dimensioned, and both ends are square. However, the ends, they do have a little bit of a burr. So I find this Noga deburring tool to be really handy. All you do is rotate it around a handful of times like so, and you can see the lights actually picked it up there. Look at that. Nice little bit of a relieved edge. And to shape the other end of this 5mm rod, I have chucked in a drill, and I'm going to use a belt sander to make a bullnose, a rounded type of profile. And here's the Vise stop after 14 hours in the tumble vibe at Green Pyramid Media, and that leaves a very nice matte finish. It doesn't really obscure all the milling marks by any stretch of the imagination. However, it does even out the finish, and I think it looks really quite nice. Additionally, it very, very slightly relieves edges, makes them a little bit more user-friendly. But they're still fairly hard edges. It doesn't really wear the part down whatsoever. Now let us see how we can use this vise stop. I have it mounted on this side of the vise. It is symmetrical. Could be mounted on that side as well. This slotted hole allows the vise stop to be located in a wide variety of locations, even up above the jaw, near the top of the jaw, somewhat lower, even way down at the bottom. Additionally, it can be swung out of the way when it's not being needed whatsoever. That's pretty nice. Now, I have installed the 5mm rod. I got a flat end at one end, a bull nose at the other, and I guess which one is used is going to depend on what sort of part I am locating. If it's a part that's nice and square and flat, I think the bull nose would be a little bit more repeatable. However, if it's an irregular surface like a mill finish, that flat end might be the more appropriate end to use. Now let's test it out. I have some parallels in the vise, and in case you're wondering why I did this complicated L-shaped design, well, it's to give clearance for parallels to fit underneath. Well, let's try the vise stop on this challenge piece. It's a challenge piece because, well, this side here is nice and flat. However, this side is kind of rough and, well, it's round. Anyways, let's put it in the vise, and I'm going to clamp it down good and tight. Okay, the vise is tightened down. Now let us pull the part into this test indicator and get it zeroed. Pretty good. Then I'll lock down the table, and let's swing the vise stop into position, and we're going to tighten it down. I really got to get some hex cap screws. This is a Torx screw. Torx are nice, but around the mill, I think hex keys just are a little bit easier to use. They're a little bit easier to grab a hold of. Anyways, our vise stop is locked down. Let's take the rod lock and loosen that up. We push the rod into the workpiece just like so. Lock the rods locked down. Once again, Torx screws are a bit annoying in this regard. Okay. Okay, that is now locked down. The part is still zeroed. It should be because it's locked good and tight in the vise. Now let us open the vise up just a touch. Take our part out, and I don't know, we need to do something with it. Mark it up, just check it for the progress that's going on, and drill it, something like that. And now let's put it back into the vise, located with that vise stop, and we're going to lock it down. And voila, back into position. Maybe off by 1/100 of a millimeter, but that's probably something to do with that rough surface. Anyways, thanks for watching. I hope you found this useful, entertaining. Subscribe, and I'll see you next time. Bye-bye. Bonus footage. Is this vise still trammed? Has a lot of tightening and loosening and tapping and lateral forces and... Woo! Not too bad. 1/100 of a millimeter.